Hello class, we're getting closer and closer to the end. Unit 6, Lesson 2 here. We're talking about period of simple harmonic motion. Last lesson we briefly covered what period meant and its relationship to the frequency of simple harmonic motion. Now we're going to get a bit more mathematical about it. So in order to determine the period of a mass attached to a horizontal spring, physicists were able to show the periodic motion of the mass is equivalent to the horizontal motion of a mass going around in uniform circular motion. And I'll attach you a video that really clearly shows this connection. It's really neat. It's kind of hard to see just on paper, right, without it moving, but when it's actually going through its motion, it's really clear to see that when we're just analyzing one component, right, like the x velocity, we're actually seeing a really direct relationship between simple harmonic motion and our uniform circular motion. So if the radius of the circle is equal to the displacement from the equilibrium, right, so from the center of our circle, right, to the outside of the circle, that's either our radius or our displacement. They are actually the same value in this case. And that would be at its equilibrium, right? Zero displacement, because we have no displacement in this x direction. And at this point, right, now we are fully to the right, right? So our radius would be this displacement from equilibrium to the right. So this illustration is okay. Some of you might be able to already see this connection here, but the video will make that much more clear. So we see a big connection to uniform circular motion and our simple harmonic motion of a horizontal mass on a spring. So at both points 1 and 3, we have maximum acceleration. And if we're still running with our analogy to uniform circular motion, that acceleration is equal to our centripetal acceleration. And because those are actually equivalent, we can put together the acceleration of the mass, which is from our spring, right? And the force of a spring creating an acceleration leaves us with this part of the formula, right? This was from last class. The acceleration of our mass is equal to the stiffness of the spring, the K, times its amplitude or its displacement from equilibrium divided by the mass of the object. And since the centripetal acceleration is equal to that maximum acceleration of the object on the spring, we can put down what we know about centripetal acceleration in uniform circular motion in terms of period, right? So 4 pi square r over period squared will leave us with this formula, right? And radius is equal to our displacement from equilibrium. And we can rearrange it into this slightly difficult to work with equation with the square root in there and all, right? So we would multiply both sides by period squared, right? We would then divide by k multiplied by m, take the square root, and we're left with this formula for the period. So from here, right, all we need to know is the mass that's attached to the spring and the period of the oscillation. And if with the mass and the spring constant, we can find period. And with period, we could find frequency. So there's a lot of connections between these formulas. So far, we've only gone over 3, and we already have a lot of connections, as we'll see shortly here. So that's it for the notes. We're going to get right into examples. I do encourage you to watch the video that does a better job of demonstrating and visualizing this relationship, right? And we're just doing some good physics, right? Combining the conceptual idea of this circular motion being analogous or pretty much identical in its x direction to this horizontal spring. And since they are identical, we can actually set their accelerations the same and derive this formula. So if deriving the formula isn't coming super easily to you, don't worry about it. You're given this formula. You'll be able to solve for period using mass and a spring constant. So let's try our only example for the day together. We have a cart which is attached to a spring undergoing horizontal circular motion. So if you want to draw it out, right, we would have our max compression, our equilibrium, and our max stretch with this distance from equilibrium or amplitude for each of them. So it gives us the mass of the cart, which is 5.7 kilograms. It's going through horizontal simple harmonic motion, which is almost the same as our x component of our circular motion. Right, just trying to make that connection between uniform circular motion and simple harmonic motion, right? If we're just looking at the one component of it, then they are actually more or less the same, right? So this would actually be the radius, right? And we're at equilibrium and a radius there. So they give us a mass. They also give us an oscillation frequency. So we know it's a frequency because it's in hertz. Even if the question doesn't explicitly tell us, whenever you see hertz, we know we're working with frequency. So we've got 2.61 hertz as our frequency, and we were trying to find K, stiffness. So we know we have our formula, the hybrid of uniform circular motion and simple harmonic motion. Period is equal to 2 pi times the square root of mass divided by stiffness. This is what we're looking for. We need period, first of all, right? We know the mass. We're looking for our stiffness, our spring constant, but we need this. So that's going to be our first step. We're going to find period. Remembering that period is equal to 1 divided by frequency. So 1 divided by 2.61 hertz, right? Where a hertz is actually 1 over seconds. So we can see our units work out here. 1 divided by 2.61, 1 over seconds, gives us 0.383 seconds. And that's going to be for 1 cycle. So every cycle takes 0.383 seconds. So when it goes out and back in, right, that's going to take 0.383 seconds. So it's going pretty fast, right? It's doing almost 3 of those every second. 2.61 to be exact, because that's our period, right? So there's a close connection between period and frequency, and we need to really get that understanding really solid in our heads. So now we know our period. We're going to do some fairly difficult algebra. So I'll walk through it nice and slow. So period is 2 pi square root of m over k. So if we're looking for k, we're trying to get it by itself on one side. It's in a square root. So the first thing I'm going to have to do here is take the square root of both sides. So by taking the square, or squaring both sides I should say, I'm getting rid of the square root, but I also have to remember to square what's not in the square root. Right, so on this side it's easy. We've got t squared, but we have to remember to square both the 2 and the pi. So we get 4 pi squared. And now our square root is gone, and we're left with just m over k. All right, we've got rid of our square root. Now we have squares. That's okay. We're trying to solve for k, so I'm going to multiply both sides by k to get it on top where I can actually solve for it. Right, so now I have these canceled out, k times period squared. I'm going to divide both sides by period squared. Right, so those will cancel out, and I'm left with my spring constant by itself, ready to be solved, is equal to 4 pi squared m, k's have canceled, over period squared. Right, this is fairly difficult algebra. You're going to be doing it a lot though, so remember to apply your square to all aspects of our equation in order to cancel out our square root. Don't forget about the 2 pi becoming 4 pi squared. That might be an easy mistake to make. Here we have it solved for our spring constant, and now we're able to put in the values we know for mass and for period. So spring constant is equal to 4 pi squared times 5.7 kilograms divided by 0.383 seconds squared. So I need to remember in my calculator to square the pi and to square the period. And that will give me 1,532.9 newtons per meter. And if I want significant digits for that, right, my spring constant is, 1.53 times 10 to the 3 newtons per meter. And that's a wrap for lesson 2. I hope the algebra treats you well. This one add a little bit of conceptual and a little bit of mathematical. Good mix. Nice short lesson. Make sure to check out the video for a nice visual of uniform circular motion versus simple harmonic motion of a horizontal mass on a spring. All right, good luck with the homework.